Chapter 10, Correlation and Regression. So this chapter is going to it's kind of a pretty big shift in what we've been doing. We've been dealing with a set of data, and it's usually just one set of data, a family of data, and then we did some analysis on it, we did some descriptive statistics on it, and then we did some inferential statistics on it. Now we're going to switch gears and take a look at a different kind of data, and the kind of data that we're going to look at is paired data. Now, when I say paired data, it kind of sounds like that last thing that we did in Chapter 9, where you have a before and after kind of set of data. The paired data here is a little bit different in the sense that the two things, the first and second number in the pair, are not necessarily the same thing. They are not of the same unit. They could be the weight versus the height. They could be the systolic versus the nurse. Is there a nurse in there? Systolic and diastolic. Thank you. The systolic versus diastolic measurement in your blood pressure. They could be for babies. It could be the circumference of the head versus the weight and things like that. So those two are not something that we would use last chapter's paired data comparison on. So this is something different, and I would have to say it's something totally different. Some statistics course start off using studying correlation and regression and things like that. So we start off with regular data, and now we're looking at paired data in Chapter 10. So it's only going to be one chapter of paired data. Can't move. So correlation is, there's a more formal definition. I don't know if you guys are starting to write it down already, but there's a more formal definition a couple of slides from now. But correlation is a relationship between two things. They say two variables. And so what we want to try to do is we want to use mathematics to try to describe that relationship, to give it a quantity, and then see what kinds of conclusions we can infer. So our study in this whole chapter would be the study of a linear correlation. There are other types of correlation that exist and that are studied, but for us our focus is going to be on linear correlation. So we are going to define a variable r that's going to be equal to some value, a number, and that is called the linear correlation coefficient. Sometimes we'll just call it the correlation coefficient because we know in this chapter that all we're going to study is linear stuff. And that number quantifies, which means it gives, you can be given a number to figure out how linearly correlated, how much of a linear relationship you have between the two variables we're looking at. Now the formula for this is going to be horrible looking, and fortunately we have our calculators to compute the linear correlation, but when we see some of the examples in the slides here, we'll see that we're going to have to use, they use some complicated formulas, and that's what we used to use before we had calculators, or before calculators were used a lot in statistics. But fortunately, we have technology to compute all that stuff. Linear relationship means if you were to plot this on a grid, then we're looking at how much your plot looks like a line. There are other types of correlation, like exponential correlation is a really popular one, where instead of looking at the relationship as something that looks like a line, maybe the relationship looks more what we would call exponential. And a lot of things like population growth, bacteria growing in a petri dish, they follow a different model of correlation that's not necessarily linear. And so there are other types of correlation. Like exponential correlation, and many more. There's, if you remember any of your functions from algebra, then it's all quadratic, cubic, and all that stuff. Logarithmic, those are all types of correlation. All right. We'll start with the basics. If you guys already didn't write it down, and this is just another way of restating. Correlation exists between variables is if one of them is related in some way to the other. I wish I would have wrote down the website. There's this website that somebody sent me about false correlation of things. They find like relationships between two things that statistically have a high correlation, but totally has nothing to do with each other. One of them is New Orleans. I don't know if it's the whole state of Louisiana or some other smaller city there, but they say that New Orleans over the years is having more and more people populate it, and also New Orleans is sinking, going below sea level, and so there's this myth that there's a correlation that there's more people there, so that it gets heavier and starts to sink. That's not really the case. The reason why it seems like the sea level is going down is because maybe the sea level is rising. I don't know. But some silly thing that people can make up because there's a statistical correlation, but there's going to be some caveats with these correlation problems, in that you can't always conclude that one is moving the other to do something else. All you know is that there is a relationship, and we don't know what the relationship is. This also was defined in a previous slide. The linear correlation R measures the strength of the linear relationship between the X and Y variables in a sample. So this is the X and Y variables that you might have seen before in your algebra classes or whatever, where you would plot points, you'd plot X values and then Y values, and then this is how the ordered pair comes about. So it's important to understand the type of data that we're moving. I don't know if you guys can see this already, but when we see our first example, you'll actually get to see the type of data that it is we're looking at. And so a scatter plot, let's see. A scatter plot would be a two-dimensional plot. Let's pick a simple XY problem, 1, 1, 2, 3, 3, 1, 4, 2. As an example, we would plot these points, and normally in like an algebra class, I tell the students to always label your points that you're plotting, but sometimes you get a whole big bunch of plots that you don't want to care too much about labeling. So we'll do that. So 3, 1, and 4, 2. So usually we label X as the horizontal axis, Y as the vertical axis, and then you would plot these points and they would look something like this. And so the question is, how close does this look like to a line? a lot of times you're going to see in actual data that it's not going to look anything like a line. You know, a line has to pass through those points, but you know, it doesn't make sense for us to draw a line like that would make it pass through those points. So what we can do is we can ask ourselves, how close does this look like to a line? Is it close? And if it were close enough, can we draw a line that would kind of best fit the data? Would a line like this best fit the data? I don't know. It hits those 2 points, but then it kind of neglects these other 2 points. So maybe a line more towards the middle between them might fit the data. So in the next section, we're going to be interested in finding equations of these lines that might look something like this that would fit the data the best. And then we're going to study lines a little bit, the slope and y-intercept. I hope that sounds familiar to you. If it doesn't, we're not really going to call it a slope and a y-intercept. We're going to call it A and B, which is what they call it. So there are going to be some switches in notation depending on what technology you're using. So we'll try to be as consistent with the textbook as possible. So here are some examples of some more scatter plots where there's a lot of points, and usually that's what we're looking at, is a whole bunch of points. And then in these examples over here, they give their R values, the correlation coefficient. So if you get every single point on your data set to fall into one straight line, then that is a perfect correlation. Now, negative, positive just tells you the slope, which way is it going. And the way to look at the slope is that if you go from left to right, and then you see that you're moving up, then it's positive slope. If you go from left to right, and you see that your graph is moving down, then that's negative. So that's the difference between positive and negative. In reality, we don't get a perfect correlation. Positive and negative correlation, yeah. In reality, a perfect correlation is hardly going to exist. So what they do is they give these values. If your graph kind of looks like it's falling onto a straight line, and it's not perfect, but it's really close, all those points are really tight right next to the line, then you have a strong positive correlation or negative correlation depending on what the value is. If it's a little bit more scattered, you can still have a pretty good correlation as long as they look like they're all following a straight line. So if you look at these numbers, you can kind of get a scope of what those possible values for the correlation coefficients might be. So in a few slides from now, we'll see that the R values that you would get are going to be between -1 and +1. And it's going to be -1 if it's going down, negative. It's going to be +1 is perfect going up. And then everything else can be in between. Now, 0.85 is actually, or even 0.7, is actually very good correlation. So you get something that's more close towards 0, then that's not very good correlation. And there are a couple of examples of that as well. Something like this where I don't know how to draw the line that would best fit this, a straight line or a horizontal line, line going down. So there's not a good line that would best fit this data, and so this is an example where you don't have a correlation at all. You have 0 correlation. Or anything close to 0 is not very good correlation. This one is an example of clearly it looks like a shape that we might be familiar with, but if we're talking about a linear correlation, that's not a very good linear correlation. So this is 0.087, so that's really close to 0, and we can say that that's really bad linear correlation. But if you step back and look at it again, without restricting yourself to being linear, this looks like it follows, in math, I guess what we would call this a parabola. So this would be a better modeled by using a different type of function instead of a linear function. This might be modeled better using a quadratic function. We don't need that for this class, but it's a parabola, it's quadratic, so second degree polynomial, what we would call it. So we might be better off using a quadratic function to model this thing. Okay, so we haven't dove into how to find the value of R, but right now we've gotten a few good examples, a few good glimpses of what R could be and what R should be. So a good exercise is to take a look at a data set and then try to guess what R is equal to. So maybe like in this slide, maybe I should have crossed all these things out and then asked you, what do you think R would be in this case? So that's usually a good thing to do. And the exercises that we're going to be doing for the sake of time, we don't have very many points. Something like this, it looks like there's over 30 points in there, which is a good number to look at, and then you can see the correlation. But when we have less and less points, it's harder to guess the correlation. So we will be doing a hypothesis test on this, and the question we're going to ask is that if there is correlation or not. And so keeping in rhythm with the rest of the hypothesis test that we've had before, we start off with some requirements. And so the requirements for this particular section is asking us to make sure that we have paired data, an X and Y, and then that simple and random business again. So the sample of paired data is random. Visual examination of scatter plot must confirm the points approximate a straight line pattern. Now the third part is not something that we would normally do in this class, but in real life situation, if you're collecting data and then you see you see a bunch of points that look like they're all pretty much lined up, and all of a sudden there's this one extra point out here that just out of nowhere just kind of appears over there. So those are what we would probably call outliers. And if you include this point in your analysis, then that's going to really, it's like the mean, right? One point can really move the mean and standard deviation quite a bit. So that's the same thing over here. One point that's not within your norm is going to move your correlation coefficient quite a bit. And so we want to make sure that if we ourselves are collecting that data, and then you get this thing that's way out here when you do your scatter plot, you want to look at it carefully again to make sure, is that really a valid point, or is this one of these points that we can probably eliminate because it looks like it might be an outlier? So that'll be your choice. And most of the problem that we're going to be doing in homework and quizzes and in the test situation, you're going to keep all your points. We don't need to worry about outliers, but this is just for you. Now, I don't think you need to worry about this particular page, but this page is preparing you for another crazy page of formulas that, again, you won't have to know. I do, if there's anything that's important here, I would circle these three things. N is the number of pairs that we have. It's been our sample size all along, and so it's not any different except you're counting pairs. So you have 1 pair, 2 pair, 3 pairs, all the way up to n pairs. R, we already talked about R. That's your correlation coefficient. But just to be formal about it, that's your correlation coefficient for your sample. Now, this other one is not P. This is not the letter P. And for most of our population parameters, we've been using Greek letters to represent our mean or standard deviation. And so this is a Greek letter R called rho. And if you were to write capital R, you would see our regular R that we use in our language. But if you use a lowercase r, it would be like this. And so this is rho. So when you do your work on paper, I would like you to not write this like you would write a P. Okay? So do something where it's a little bit different, like put a little tail on the bottom or something like that, or make it look like just a little bit different from a regular P. So make your rho look a little bit different, and then as I'm looking at your work, then I'll know that you meant to write rho instead of P. So rho is going to represent the linear correlation coefficient for the whole population, which, like all the other parameters that we've looked at, we'll never know. We'll never know what it is for real, but we're always going to be striving to estimate it, and so we'll use the sample. Okay. So this is where you say, thank goodness for technology. So the linear correlation coefficient is this, and if you can compute all these things, you can find it, and I just don't want to see this on paper. You guys are doing your exams. Don't try to use this formula because, one, it'll take you a long time. Two, there's a lot of room for error. Three, you guys get to use a calculator, so no need to worry about this. But this is how the formula would look like if you didn't have a calculator. So again, thank goodness for the calculator. And computers can compute it too. Excel can find your correlation coefficient. All right, so I'm going to go past that. The correlation coefficient is much like the test statistic that we've had. And to do a hypothesis test, we would compare it with a critical value. And so here the critical value, I don't know if it's A6. I think it's A5. So the idea is that you can use your correlation coefficient R and then compare that with a particular critical value. It doesn't say critical value here, huh? So table A5 or A6, it says A6 here. I didn't check earlier. I should have checked. It's the Pearson correlation. The other one is it's called something else, but if we're going to need something, we're going to use a Pearson correlation. So I don't know if that's 5 or 6. But anyways, you're going to use that. That's one way to approach these hypothesis tests. The other way to approach the hypothesis test is that when we do our correlation, when we do our hypothesis test on the calculator, we're going to find our p-value. And so we're going to stick with that p-value method where we compare it with some sort of significance level. And so that's just going to make our lives a lot easier. The round off rule for this is because the table has critical values rounded off to 3 decimal places. You too should round off your correlation coefficients to 3 decimal places. I keep saying here, use a calculator or computer. Almost every slide. Okay, 3 decimal places. That's easy enough to remember. So here's an example, and don't bother writing down this example. I'm just going to go fast. We're going to do another example that I'm going to take from the homework. But anyways, here's a small set of data, 4 pieces. And so this is how you would normally do this calculation, and this is to do it without a calculator. You write your x and y in columns, and you would kind of start off with the 2-column x and y business, and then you're going to start extending your column. So a couple of things that you need to do is you need to add up all the x's and all the y's separately, because that's a piece of the formula. You can multiply the x times y and start a new column, and then you also need x squared and y squared, so you can do all those values. And then eventually add them all up. And so these are these weird numbers that you saw in that formula that I told you not to write down. And then so in that formula, you would just punch in these numbers, 12, 23, 61, 44, and 141, and then do your calculations. So there's an n. There's this thing, there's this and this, and so and this is really what throws a lot of people off back in the old days before they used calculators. Is that there's one where you add up the squares, and there's one where you add up the x's and then square it, and they sure look alike. And so when people do these computations, this is one of the big pitfalls and big places for errors. But anyways, the bottom line is that you're eventually going to get your correlation coefficient, and then this is your correlation coefficient rounded off to 3 decimal places. Now, 0.95, without looking at the table or anything like that to compare, 0.95, does that look like it's a strong correlation or a weak correlation? Strong correlation. It's close to 1, or it's actually close to -1. So it looks like it's a strong correlation. It's a negative correlation, which is also something that's important to observe. So it looks like we have a strong correlation. Now, based on this number, we would want to compare it with a value. So this is where I would take the table out, which I should have had earlier, and I didn't prepare it. Pearson is Pearson. So it's A5. A6 is Spearman's. So we're going to do Pearson. So it is A5. So going on this thing, this is our table that we would be looking at. And notice that the table is a lot slimmer than the other tables that we've seen. So the idea here is that these tables are now restricted to just 2 significance levels. We're only looking at 0.05 and 0.01, so we're not going to bother with the other stuff, because usually 0.05 is going to be our a value that we would be looking at. So if we take a look at the problem that we were actually doing, we got 0.956. So depending on whether we're looking at an alpha is equal to 0.05 or 0.01, if alpha is 0.05, then we would compare this critical value with the 0.05 value that they have. So the degrees of freedom we haven't talked about. Oh, this actually won't work. Because what's n in our problem here? Well, n is 4, right? Oh, no, n is 4 right here. It wasn't degrees of freedom, sorry. Degrees of freedom here is we'll worry about that later. So n is equal to 4, and then your value that we would want to compare to is 0.95. So we want to ask, how does this compare with 0.95? Your values, critical R values, would be would be 0.950. So what we would do here to actually measure or formally test this, actually I should knock off the arrows here because technically it doesn't go on forever. Your critical value, your correlation coefficient is bounded between -1 and 1. Not quite drawn to scale, but I would say, let's say 0.95 is there, and I would be curious to see where this value is. So this value is -0.956. It would go right here. And so that's closer to 1 than our critical values, or in this case, closer to -1 than our critical values. So we would say that it looks like there's correlation. It looks like there's strong correlation in this problem. Okay, but we'll get more formal on this. There is correlation. Up here? Maybe. Critical R values. Yeah. Table A5. That doesn't look like a 5 anymore. All right, we'll do another example from our homework. We'll do one after we get over a few more slides here. Skip over that. So we've already seen, and now we're kind of listing it down as a property. We're already seeing that the critical R value, or not the critical R values, but the correlation coefficient values go between -1 and 1, inclusive. So it could possibly be -1, it could possibly be +1, and it would happen to be -1 or +1 if it was perfect correlation. Otherwise, it would be somewhere in between. Now, here are a couple of other interesting aspects of this correlation coefficient. If the value of R, does not change if either value or either variable is converted to a different scale. So if you're comparing heights versus weights, for example, and then you have weights in pounds and then heights in inches, and then for some reason somebody decided to change the height into centimeters, then your plot, the way your plot's going to look might change, and some of the other values that you'll change might change, but the correlation coefficient will still be the same. So if you change the units for one of the variables, you're still going to have the same correlation. Because it shouldn't depend whether you're measuring in inches or centimeters, right? You're still measuring something. So your correlation coefficient will still be the same. The third property here, the value of R doesn't change either if you switch the X and the Y axis. So if you made the X's the Y's, if you made the Y's X's and actually switch them, then your graph is going to look different again. And some of the other values from your graph will be different. But your correlation coefficient will still be the same. It measures the relationship and not knowing which is dependent on what. So the correlation coefficient just measures the relationship. And then the last thing that they say here is something that we've already discussed, that the R measures the strength of the linear relationship, not any other possible relationships that might exist. So it could be exponential, it could be quadratic, and we're not going to know that measurement using R because R only looks at the linear relationship. So these are the basic properties of your correlation coefficient. R squared, we'll come back to R squared later on. Let's deal with that later. Here's another worthwhile slide to discuss. When people are doing correlation coefficient problems, when they're doing scatter plots and they're finding out whether something's related to the other, sometimes they assume things. So if there is correlation, some people might think, oh, then one thing is causing the other to happen. I think we already talked about that a little bit earlier, to say that if you find a relationship between two variables, you're not going to be able to identify what the cause is of that relationship if one is causing the other variable, one variable is causing the other variable to act the way it's acting. So that's causality is a common word for that, and it's a common error in statistics in general. When you take averages of things, it might look like the correlation might be closer than what it actually is. So we don't want to do that. And then again, there might be some other relationship between the variables that's not linear that we're not seeing. So all these are more theoretical and conceptual problems that you would apply if you were to use this in your own real life situation. But in terms of our class, I don't think we need to worry too much about identifying these common errors. Might be a good thinking question, though. I usually have one page in the final exam that's more kind of like theoretical thinking question definition. So this has never made it to my final exam, but it might. This is an interesting page to look at to make sure that you're being careful about making conclusions that are appropriate. All right, hypothesis test. So this is where we actually do a hypothesis test. So the test is to test if there is correlation. So this is going to be, it's going to look like our usual hypothesis test, but it's going to be a slightly different in a sense that your null and alternative hypothesis will always be set up like this. We will never look at a greater than or a less than possibility. It's always going to be like this. Your hypothesis test, your null and alternative hypothesis will always be like this. And then the claim is that there is correlation. So the claim is that there's significant correlation. I should put linear here. There's significant linear correlation. And so your claim is the null or alternative hypothesis. And it looks like the alternative hypothesis, right? So your claim is alternative hypothesis, which in that flow chart is moving you to the bottom two boxes. So your claim is your alternative hypothesis. It does not contain a condition of equality. So your conclusions are one of two things. You're either going to conclude that, yes, you support correlation, or no, you don't support linear correlation. We'll get to the conclusions in a little bit. So when I say test for correlation, I'm probably not going to state, test the claim that there's correlation. I'll just say test for correlation, and then you should assume that your claim is this. And I don't care if you write this down, but I do care that you write down your null and alternative hypothesis, because it is a hypothesis test after all. When we're doing a hypothesis test, remember, I look for three things. I look for the null and alternative hypothesis. I look for the work that you do to calculate your important values like test statistic or p-value, and then I look for the conclusion. So I need to see at least this for your first step. Yeah?
So if it's not zero, it's always.
If it's far away from zero, yeah. It doesn't go past 1, so the closer it gets to 1, the more significant it's going to be. Yeah.
So that's how you define significant.
Well, the way we're going to define significant is, one, we're either going to use the p-value, and so significant is that if you have a small p-value, and it becomes significant. Or if you're going to use the correlation coefficient, you're going to see how close it is to 1, but you're going to have a critical value from table A5 to compare it to. Yeah. And we'll see a nice graph of that. The book also talks about a t-value, or what do you call it? A traditional method using the t-distribution. We're not going to use that. So I'll try to remember to cross that out, like right here. So this is in your book. I don't think you need to worry about this. So this is the hypothesis test business. It kind of streamlines your 8-step process. And if it was me, I would be talking about a 3-step process. This is your step 1. To write your null and your alternative hypothesis. All this stuff over here kind of falls under step 2. Here they talk about the traditional method, they call it, method 1. I'm going to cross that out. Say I don't want you to look at that. So you can do one of two things. Method 2 is described here is to use the R value to compare it with a critical value. But you can also use the p-value. And the p-value you would compare with alpha. And so that's usually a lot easier to deal with. And then our last step, step 3, is to reject or fail to reject the null hypothesis. And then if you rejected the null hypothesis, then there is linear correlation. So this last 2 sentences kind of fall under the last 2 boxes of that flow chart the final wording. But if you just, you can consider this like a special set of phrases that you would use to write your conclusion. And all it's saying is that there is linear correlation or there is not linear correlation.
What's the absolute value of that for all of it?
Where?
If the absolute value of the test,
Oh,
or that,
it'd be better if we look at the graph. So let's just, we'll take a look at an example to see what they mean by absolute value. I'll talk about the absolute value business. So this because of technology, this becomes a lot shorter and a lot easier than what we've had in the past. And since we're really restricted to just one of two choices, we only have one possibility for our null and alternative hypothesis, and then that kind of slims down our conclusions to only two possibilities. There either is correlation or there is no correlation. As simple as that. Seems easy enough, yeah? Okay. Let's see. Now this is the part that I scratched out there, but I'll leave this one on here for now. So I'll just put a little note here: don't use. But the reason why I want to leave it is because there's something interesting about this. It turns out that degrees of freedom for Chapter 10 type problems is different from what we've been used to. You know, we've always been used to seeing n minus 1. All of a sudden, the degrees of freedom is n minus 2. So that just makes it a little bit different. But we're not going to worry too much about that because, like I said, I prefer that you don't use this method. This is going to require you to find a t value, compare with t, critical values and stuff. Not needed, not needed. So the method that they have here is using the R method and comparing it to a value from table A5. Again, it's the Pearson correlation. And what they mean by the absolute value is that because this thing is symmetric about 0, and if you remember, we took a quick look at that table. All the critical values from that table are all positive. But when we compare it to a correlation coefficient, because the correlation goes between -1 and 1, we want to include the negative of that critical value as well. And so what they mean by the absolute value is that when you finally plot your own R correlation coefficient that you found, if it's over here, then technically on the number line, your R critical value is less than, your R value, your correlation coefficient, is less than the critical value. But if you take a look at the absolute value of that, it's going to be greater. So that's what they mean by the absolute value. But you can totally avoid this information because it's really not that necessary. And again, I'm going to try to push you towards using the p-value method because our calculator does the p-value for us. Okay, so let's in terms of that picture that I was trying to draw, this is this is the picture that I was wanting for you guys to see. When you're using the R method and you're looking at the critical values, so remember that your number line is only restricted between -1 and 1, and 0 is right in the middle. When you find your critical values from the table, A5, you would mark them over here. So anything from your critical value to 1 or your critical value to -1 on the left side would be rejecting the null hypothesis. Anything in between your two critical values that include 0 would be failing to reject the null hypothesis. And remember, if you fail to reject that, you're not really accepting it, but you're saying, oh, then it's pretty much 0. And when your row is close to 0, then you have no correlation. So sometimes people have a hard time equating rejecting the null hypothesis with saying that there is correlation, but that's what happens. In these two cases where you reject the null hypothesis, there is significant correlation. And when you fail to reject, there is no significant correlation. Okay? So then that's what you would write in your conclusions. On the quiz, I think I have you write down one more piece of information. I think I will have you identify whether the correlation is positive or negative. So in the end, you would say there is significant positive correlation or negative correlation, if there is correlation. Okay, so the other way to look at this is using the p-value. And so let's do an example where we actually use the p-value, and then we'll also take a take a note at the other methods that they discuss. So get your calculators out. We're going to do some calculator work. We will do this problem from section 10.2. So it says listed below are the overhead widths of seals measured from photographs and then their actual weight. So imagine some satellite or some satellite photo that zooms in and takes pictures of seals, and then you take them and then you weigh them. So can't do that for every single seal, but if you have a sample, then maybe you can use this if there's correlation between the size, their size, and then their weight. Then you might be able to identify the weights of seals using the correlation. So it says to construct a scatter plot to find the value of the linear correlation coefficient, and then check at the 0.05 significance level to see if there's correlation. So the first thing we want to do is we want to punch all this stuff in our calculator. So let's do that. And the way we do that is with our list. So I emptied my L1 and L2. Remember, if you want to empty it, you move your cursor up to where it's just L1, and then you hit clear, and then you hit enter or arrow down, so you wipe out all the data. So let's put the overhead width in the first column and then the weight in the second column. And you have to, you type it in really quickly, and then you just, especially in the test situation, you want to make sure you double check, because one wrong number over here is going to throw off all the rest of your answers. And the first thing to absolutely check for is to make sure that both of your lists are the same size. If they're not the same size, you're going to get an error, of course, because it wants to do things together. All right. The first thing they ask for is a scatter plot. Now, in the homework situation, you'll get multiple choice and you just choose them. But it might be good for you to know how to do the scatter plot on the calculator anyway. So there's a nice, easy way to do this. For that, we're going to go to second function and stat plot. And let's just say if you have any of your plots turned on, just go ahead and hit 4 to turn all the plots off. I'm going to go through that motion, hit 4, plots off, and then enter. That just makes sure everything is off, and so I don't have to mess with it. Second function and stat plot, and then I hit the number 4 to turn plots off, everything off. You have second function and y equals. All right, so we're going to work on the first plot, plot 1, so let's select that one, and let's turn that one on because you just previously turned everything off, at least I did. Arrow down to the type, and the type that we're going to get is the first one. So while it's there, hit it, or hit enter, so now it's blinking on that particular icon. And then arrow down again to the next set of questions. It's asking for the X list. My X list is in L1. So I would press second and the number 1 if it's not already L1. Your Y list should be L2. Mine right now is L3. So I'm going to press second function and the number 2. Now your mark, you have 3 different possibilities for a mark. The easiest one to read is a square, which is the default. And the idea behind the other 2 is that if you have more than one scatter plot that you want to compare, then you might want to have a different marker for them. But for us, we'll just use a square. Okay? All right, now let's go to zoom and look for zoom stat. What this calculator is going to attempt to do with the zoom stat command is it's going to look at the statistics, and it's going to decide how to set your window. And so now this is how your scatter plot would look like. Stat plot, if you go to second function and the y equals 2, that one should be on because we just turned it on. And it should say L1, L2, and then the little square thing there, right? So I'm going to hit that again. This time I'll take screenshots of this. Zoom for zoom stat. Oops, how come it didn't go in there? All right, so you could probably look at this and compare it with the choices in your homework set. I would probably, not the first one, not the second one, the third one, and the fourth one look kind of close. So we have to look even more carefully here. The highest number here is 245. This looks like it creeps up closer to 300. Suppose we can also get a closer look. So 200 would be over here somewhere, and 245 would be right around here. So I'd probably choose C between these two for my values. And you can't do this without actually doing the scatter plot on your calculator, but you know, why not? You're doing it anyways. All right, so that's our first one. Now it's asking for a linear correlation coefficient. So let's go back to our calculators. And now we're going to do another test. So let's go to, I really want you guys to follow me on this one. All right. Let's go to stat and test and look for lin reg t-test. So the lin reg t-test is it's a linear regression, and it's a t-test because that's how normally it would be measured. But we're not going to use the actual t part of it because we can use the p-value to help us find the value. So lin reg t-test, select that. It's going to ask you where your X list and your Y list are, so you're going to put L1 and L2. I have L3 here for some reason. I'm going to change it to L1 and L2. Your frequency is going to be 1. Now, what do you think this next one's going to be? Not equal to, right? So it's not the less than or the greater than. Because remember, when we're doing this, we only have one possible alternative hypothesis. Now for the reg EQ, do you guys have something there? Okay, so you only need to do this once unless you accidentally erase it, and then you'll have to do it again. But when you get to the reg EQ, you should put Y1 in there. Because what that's going to do is it's gonna create your linear regression line, the line that best fit the data, which we'll talk about in the next section, and then that's going to place it into a special memory in your calculator that we're going to be able to access. So while your cursor is blinking over here, go to vars. Vars is right next to clear. Go to the right where it's yvars and select that first one where it says function, and then y1. So just hit enter or hit the number 1. And now you have Y1 for the reg EQ. And what that's going to do is it's going to keep track of our equation. And I'll show you where that equation is later on. All right, let's calculate. And when you do the calculate, I really want two numbers, but I suppose it doesn't hurt to write down three numbers. The first one is your test statistic for your t-value, your critical t-value for your, the first one is your test statistic. But we're not really going to need that. But if you want to identify that, you can. And then the one that goes after that is your p-value. Now, there's an arrow, right? An arrow pointing down, so you know that there's more stuff. So scroll down until you see more stuff, until you see the end of more stuff. And then you'll see, eventually find your R. So your correlation coefficient is all the way at the bottom. Your test statistic is the first one. Your second one's a p-value. You have your degrees of freedom, if we're interested in looking at degrees of freedom. And then you have two other important numbers that we're going to take into consideration here. We'll talk about later on. But for now, the correlation coefficient is what we're looking for. So R in this case is equal to 0.940. Yeah, the more, the better, actually, unless you're doing your homework. Let's try round it off to 3 decimal places. Let me try rounding off to 4, see if it bothers me again. 9404, let's try 0.9404. Nope. Three. And now the critical values, this is where you would need to go to the table. And for the test situation, I don't think you need to do that. But for the homework purposes, it'd be good to know how to use the table A5. Now, for some reason, I keep saying A6 here, but oh, you can click on this, huh? So the degrees of freedom, what's the degrees of freedom? Actually, we don't need degrees of freedom, sorry. We need just the sample size. What's the sample size? There's 6 of them, and our alpha is 0.05. So I think that's 0.811. But here, they say find your critical values, use a comma if needed. Well, there's always a left and a right side for this. So it's the negative 0.11, comma, positive 0.11. So now we can try to make our conclusions here based on our critical values. So let me get the critical value, let me get that part of the page going on here. If we were to use the critical values, because we found them anyways, You would draw your table like this. You don't have to draw it, but I think it's always good to be visual about this. And then you find your correlation coefficient. Draw different color. You take your correlation coefficient. R is equal to positive 9.940, and you see where that lands. So compared to your critical value, it's closer to 1, right? So it looks like you reject your null hypothesis. And so you're supporting your claim, or you're supporting the alternative hypothesis. So there is correlation. So because the absolute value of linear correlation is bigger than it's larger than the critical value, there is sufficient evidence to support the claim that there is correlation. Yeah, so you're comparing R to a critical value. And the way I would like you to look at it, instead of thinking about absolute values, is that compared to your critical value, this is your R value. Take your R value, and then you plot it in this number line. If it's closer to 1 than the critical value, then there is correlation. If it's closer to -1 than your left side critical value, then there's correlation. So there's correlation if it lands in the space here closer to 1. And there is no correlation. What color? Gray. There is no correlation if it lands around 0. Oh, that would have been easier. So just like before, we would compare the p-value with alpha. The p-value is 0.005. Alpha is 0.05. So the p-value is less than alpha. Whenever the p-value is less than alpha, what do? Reject the null hypothesis. And so that's the same conclusion that we got here. And the only thing you need to remember is that if you reject the null hypothesis, then there is correlation.
So do you want us to do or compare both the R value to the critical value and the p-value?
In a test situation, I'd be happy if you just find the p-value. I will be asking you for the correlation coefficient, though, so you need to write that down somewhere, but I don't think I'll be asking you for the critical value for that R. Okay, so this is a complete hypothesis test. This basically packaged things up. Again, it's not, oh, I didn't do my hypothesis test with a null and alternative hypothesis. So if I want to completely do this hypothesis test correctly, I would write my null and alternative hypothesis. I would show my p-value. I would say what I used to find my p-value. I would show my R. I would show my p-value. And then I would write my conclusion to say that there is correlation or there is not correlation. Yes? never remember that equal sign. I think so. If this happens to be equal to the alpha, then you would say it's okay. You also reject it. I think. But yeah, it won't be that big of a deal. All right, questions? Yeah. N equals 6. Alpha, you also need alpha, so you need two things here. N is equal to 6 and alpha is 0.05. So with those two, N is equal to 6, alpha is 0.05, so it's this number. The thing to remember, though, is that when you're doing the homework, you have to remember that there's negative and positive parts. So when you put in your answer, just make sure they would normally ask to put a comma in between, so make sure that you have that negative also. Okay? Any other questions? All right, good time for a break. Let's take a break. When we come back, we'll finish the other two sections in this chapter, and I think that's it.